Today's lecture is RC circuit discharging a capacitor. Here you can see the circuit which we discussed yesterday in the last lecture for charging a capacitor. Today again we will consider the same circuit, but the difference is that the switch S in the last lecture for charging a capacitor was connected to the point A to include this source of EMF, and when the source of EMF was connected to the series combination of R and C, the current was flowing from the positive terminal through the resistor R to the upper plate of the capacitor, which was being positively charged, and the other plate which was connected to the negative terminal was negatively charged. Now when the capacitor is fully charged, we will throw this switch S to the point B to disconnect this source of EMF. So our circuit will assume this shape. Now you can see that there is no source of EMF E, and this R and C are connected in series with each other. And again, the other difference which you might see here is that here the conventional current flowing from the positive terminal through the resistor was in this direction, but here the source of EMF is disconnected and the conventional current due to a positive charge will flow through the resistor in the opposite direction. So you must keep this in mind. This is an important point. And now we proceed our lecture. The last lecture included this equation, which was arrived at by using two approaches. One approach was the law of conservation of energy, and the other one was using the Kirchhoff's voltage rule. So let's start again with the same equation. E is equal to VR plus VC. VR is the voltage across the resistance R, and VC is the voltage across the capacitor C. Capacitor having capacitance C. Now since this E is disconnected over here, there is no source of EMF, so we must put this E equal to 0 in this equation, and we are left with this equation. Now what is this VR? This is the voltage across the resistor R. The resistor R is having the resistance R, and it is carrying the current I, so the voltage drop is IR across R, and it is Q over C across the capacitor having capacitance C, and this must be equal to 0 because our E in this case is 0. Further, I is replaced by dq by dt, and all the rest is the same. Rearranging this equation, this goes to the other side, it gets negative q by c, and then separating the variables, bringing the q's to one side and t's to the other side, we get dq divided by q on the left hand side, and we get minus dt divided by rc on the other side, and then integrating the equation between the limits. When t is equal to 0, the charge is q naught. This naught suggests that it is the value of q at t equal to 0, and since this capacitor had been charged to its maximum value, So this Q naught must be representing the maximum charge on the capacitor. That is, initially we start from the maximum value of the charge on the capacitor because it had been fully charged. The source is disconnected after the capacitor is fully charged. So these are the conditions. We will integrate it between the limits Q naught to Q, where Q is charge at any instant of time t. This gives us natural log of Q, this integral, and here we get t, and minus 1 over RC is constant, so the integral reduces to minus t over RC with the lower limit yielding 0 result. So again here evaluating this integral between the limits, putting the upper limit over here minus the lower limit over here, we get this thing, and then this difference can be written as log of Q or Q naught is equal to minus t over RC. How will we remove this thing? By raising it to the base e, we will be left with Q or Q naught over here and the exponential term over here, because we have raised both sides of this equation to the base e. So here this thing is removed, and here we get this thing in the power of e. Rearranging further, we get Q equal to Q naught times this exponential term. Now this is the value of Q at any instant of time t. Now if we put t equal to RC, which is the capacitive time constant, then at that particular time this power reduces to 1, that is RC divided by RC is equal to 1. So we have exponential minus 1, and this gives us 1 over e. So Q naught divided by e, or 1 over e times Q naught, is actually 0.37 times Q naught. When you evaluate this thing, you substitute the value of e over here, then 1 over the value of e gives you 0.37 Q naught, and this gives you 37% of the maximum value of the charge deposited on the plates of the capacitor. So this capacitive time constant in the discharging process can be defined as the time in which the charge on the capacitor is reduced to 37% of the maximum charge. Since it is the discharging process, the charge on the plates of the capacitor will decrease with time. So at t equal to RC, the charge will reduce to 37% of the maximum value of the charge. Now once again let us recall that here the current from the capacitor, from the positive plate of the capacitor, is flowing through the resistor in the opposite direction. By opposite I mean opposite to this one, where in the charging process the current was flowing through the resistor in this direction, and after disconnecting this source, the capacitor will discharge through the resistor R in this direction, that is the current through R will flow in a direction which is opposite to this initial direction. So you must keep this in mind, and now we proceed further to calculate the current. Starting with the equation Q is equal to Q naught exponential minus T or RC. Here you can see that this charge is decreasing exponentially with time, because time has a negative sign in the exponential term. So it means that this charge Q will decrease exponentially with time. By exponential decrease, I mean the decrease in the charge is not like this, that is, it will not change with time linearly, or will not decrease with time linearly, or the graph between Q and T is not linear, but it is like this, it is exponential. Although this is the graph between V and T, but the charge also decreases exponentially, because Vc has a direct relation with Q. So if Vc is decreasing, because C is constant, so if Vc is decreasing, it means that this charge is also decreasing in the same way as Vc, and Vc is decreasing exponentially with time. So Q is also decreasing exponentially with time, and it is obvious from this equation. Now let us calculate the current. How will we get the current? By differentiating this Q with respect to time, we get current, and obviously we will differentiate the other side too with respect to time. We get Q naught, this exponential term, multiplied by the derivative of this function, in which minus 1 over RC is constant and the derivative T is 1. So this is the time derivative of this equation, which gives us I. Now here you can see, first let us rearrange this equation. Q naught with negative sign minus Q naught divided by this RC multiplied by this exponential term. This is the value of the current, and here again you can note that since this thing is constant, so this current also decreases exponentially with time. So Q, I and Vc, all the three things are decreasing exponentially with time. This exponential term has a physical significance, and it tells you that all these three quantities, that is Q, I and Vc, they are decreasing with time exponentially, not linearly. Okay, so here this negative sign shows in the equation of the current that the current is flowing in the opposite direction, which I told you that in discharging a capacitor, the current through the resistor R is in a direction opposite to that of the direction which was during the charging process. So this negative sign indicates that reversal of the direction of the current in R, the current through R. Okay, so here this is, at this point VR is equal to 0 and the current is negative, so it means that the voltage across R is now negative, or the polarity of the voltage across R is reversed, and now it is negative in the discharging process. So at t equal to 0, this graph indicates that VR is equal to 0 initially, and at t equal to 0, Vc has its maximum value. At t equal to 0, Vc has its maximum value, whereas at t equal to 0, VR is equal to negative, negative. Let me repeat it again. At t equal to 0, we see, if you uh, put some values over here on the y-axis for Vc, since this line is the positive y-axis, that is, it is above the 0 value, so the values of the voltage will be positive. And you must remember that the voltage was fully charged at t equal to 0. The voltage was charged to its peak value, so that is why if Q is at its peak, Vc will also be maximum. So at t equal to 0, Vc is maximum because Q is maximum, and let that maximum value of Vc be equal to plus 12 volts. So at the same moment, the voltage across the resistor will be negative. Due to this negative sign, the polarity is reversed, and if this is plus 12, the voltage across R would be minus 12. Now, why this is so, you must always keep in mind that in the discharging process, this equation must be satisfied. So if this has a maximum value of some positive maximum value, this VR must have the negative of that number. So if it is plus 12, this will be minus 12 to satisfy this equation, because their sum must be equal. So if this is reduced to plus 6, it would be minus 6. If this is plus 4, this would be minus 4. The thing which you should keep in mind is that the sum of these two voltages must be equal to 0 at each and every instant of time, because there is no source of EMF connected. So the sum must be 0 at any instant of time during the discharging process. Otherwise, it would be a violation of the law of conservation of energy as well as the Kirchhoff's voltage rule, because if here we apply the Kirchhoff's voltage rule and traverse it in this direction, that is, if we traverse the circuit either this way or this way, in both cases we will have if we are traversing it in this direction, we are across C. Let's start from this point. We are crossing or traversing this capacitor in this direction. We are going from the lower potential to the higher potential, so Vc will be positive, but the resistor is being traversed in the direction of current, so here the voltage drop will be negative. So Vc minus Vr would be equal to 0, and this will give us Vc exactly equal to Vr. And if we move in this direction, then this voltage drop would be, or this voltage would be positive, because we are moving opposite to the direction of I, so we will get plus IR. But this would be negative because we are moving from the positive plate to the negative plate. The voltage drop is negative, so we will have VR minus Vc equal to 0, and again this will give us Vc equal to VR. So it doesn't matter whether we traverse the circuit in this direction or in that direction, both the traversal directions will give us VR plus Vc equal to 0. So this must be kept in mind, that at any instant of time the sum of these two voltages must yield zero result. So if one is positive, the other must be negative by the same amount. So starting at t equal to 0, once again at t equal to 0 this VR is plus 12, but at t equal to 0 this VR has some negative value over here. Okay, at t equal to 0 it has got this much value. The graph is here. So as the time passes on, what happens that the voltage across R will go up and finally it would reach the zero value, whereas as the time goes on the voltage across the capacitor goes down and finally it reaches the zero value. So at any instant of time, the sum of VR and VC will be equal to 0. Let us consider the values of VR and VC at this particular moment, which may be 1 second or 2 seconds. Let's say this is a 2-second interval, the first interval. This interval is 2 seconds. Let it be 2 seconds. So at this particular instant of time, what is the voltage across C? It is somewhat like plus 8, and here it is somewhat like minus 8. Now since it is not plotted on the graph paper, there must be some discrepancies, but you must understand that at one particular instant of time this would be negative and this would be as much positive. And similarly here at this particular instant of time this would be negative 4 and this would be plus 4, and so on. So this equation is satisfied at each and every instant of time. Now let us further simplify this equation, which is for the current. Now if you replace this Q naught, which is the maximum value of Q across Q deposited on the plates of the capacitor, Q naught has its maximum value equal to CE. So if you replace this Q naught by CE, this CE, this E would get cancelled with C and we are left with E over R. So what would happen? We are left with minus E over R. I is equal to minus E over R exponential term. Now if we put t equal to 0 over here, we put t equal to 0 over here. The point which I want to make is that at t equal to 0, this VR, the voltage across the resistor R, is negative. Now this can be also derived in form of the equation. So if we put t equal to 0 in the equation of current, what would we get? This is e power minus 0 will be 1 over e power 0. Anything raised to the power 0 is 1, so this term will become 1 and I will be equal to minus e over r. So this negative sign again reminds you of the reversal of the direction of the current in R, and we will get E equal to minus IR. So again you can see that the voltage across R is negative at t equal to 0. That is over here at t equal to 0 it is minus 12. This is the zero value of VR, and as we go downward, the negativity increases, and at t equal to 0 it would be minus 12. So the voltage would be negative. Next, let us apply this equation to solve a problem, and the problem is to find the time in which the charge on the capacitor reduces to 1/2 of its maximum value. Now just look at this problem. Here it is mentioned that the charge on the capacitor reduces to 1/2. So this is obviously the process of discharging of a capacitor, in which the charge on the capacitor reduces. So we will use this equation, and we are required to find the time t in which the charge on the capacitor reduces to 1/2 of its maximum value. So the instant of time t at which the charge q is 1/2 of q naught is required to be determined. So we will put the data in this equation. We are required to find which time at which this q reduces to half the maximum value, and the maximum value is at time t equal to 0, and it is denoted by q naught. So putting this value in place of q, we will write it as half of q naught. Half of the maximum value is half of q naught, and the rest of the equation would be unchanged. So we will cancel this like term on both sides, and we will be left with half over here and this exponential term over here. Now if we want to determine t, then we have to eliminate this thing, the exponential base. And how do we do it? By taking the natural log of both sides of this equation. So by taking the log of this side, we get log of 1/2, and here when we take the log of exponential term, this e is removed. So we will be left with the term in the power, which is negative of t divided by RC. Next we will evaluate this thing, log of 1 minus log of 2, and this thing is the same. So a log of 1 is 0, so here we will get minus log of 2 equal to negative of t over RC, and then again we will cancel this negative sign on both sides. So we will get this thing, that is positive log of 2 is equal to t over RC. And since we have to find the time, then time will be equal to the product of this RC with log of 2. Now if you remember, what is RC? RC is the time constant. Log of 2 is 0.69, and RC is equal to tau c, which is the capacitive time constant. So we will write t is equal to 0.69 times tau c. Once again, to remind you, tau c is that time in which the charge on the capacitor, reduces to 37% of the maximum value of the charge. So this problem can be stated in other words as to find the time in terms of the time constant, or in how much time constants does the charge on the capacitor reduces to one half of its maximum value. And the answer is the number of time constants is 0.69. This is a little bit more than half of tau c. So in this much time, the charge will reduce to half of the maximum charge on the capacitor, that is to half of Q naught.